So, we are looking at solving flow fields using differential equations, and in previous classes we were looking at a particular way in doing them using the velocity potential equation. We introduced a small perturbation, and this was applicable for small changes, very thin bodies in subsonic and supersonic flows. We looked at Prandtl-Glauritz rule, and also in supersonic flows we found that Cp depends only on the inclination of the surface. So, that was a particular approach. Now, if you really want to solve the flow fields, it is involved and it is not very easy to do it analytically. But in supersonic flows, because of their hyperbolic nature, and they have the characteristic that information propagates in certain directions, which are known as the characteristic lines, we can use the method of characteristics which is used typically in any hyperbolic equation. It is a method to solve hyperbolic partial differential equations. In short, it is also called as MOC. So, method of characteristics. So, we look at how to solve these equations in the context of supersonic flows only, and this is the general velocity perturbation equation, which is exact and 3 dimensional. If you take it in the context of 2 dimensional cases, we have already discussed this particular equation, which is exact equation for 2 dimensional case, inviscid irrotational compressible flow. And we also had discussed that when m is greater than 1, the flow is hyperbolic, right. So, now let us look at this hyperbolic equations, partial differential equations, and method of characteristics. We have been coming across this at various times in the due course of this particular lectures. Of these lectures, we encountered it very early on when we were looking at unsteady flows. You found there are particular lines across which the solution propagates, which is u plus a and u minus a for isentropic flow. That was the unsteady case. Now, we are discussing steady 2 dimensional case. Even here in the case of the steady 2 dimensional case, if it is a supersonic flow, then the flow is hyperbolic. Here also it goes along particular lines. Now, what is the method to get these lines? We are looking at how do we get these characteristic lines. Always it is useful to go and look at some simple equation, try to understand how it works, and then further extend it to more complex situations that we are facing. So, take a simple 1D PDE, which is hyperbolic, dou u by dou t plus c dou u by dou x, where c is a constant, is given an initial value which is u0, which is a function of x. If you take the total derivative du, then if it is, and here the u is a function of x and t only. So, it can be written as dou u by dou t dt plus dou u by dou x dx. And by simple observation, we can find that if you take the lines dx by dt equal to c, then you can convert the equation, this particular equation, into an ODE, which is du by dt equal to 0. So, this particular equation dx by dt equal to c, which is also a ordinary differential equation, is known as the characteristic equation, and the consequence of which with the PDE turns into an ODE, du by dt equal to 0. This equation is known as the compatibility condition. So, now this particular partial differential equation with the initial condition gets transformed into 2 ordinary differential equations, and it is easy to solve ordinary differential equations. And in this case, it is quite simple. You just find that u is constant along the lines x minus c t. So, if take the lines x minus c t, u is constant along those lines. So, the solution just propagates along those particular lines. Now, even if we go to a more general case where you have a and b and c which are more general. So, this is a linear equation of course. So, a, b and c are consistent with the definition of the equation being linear. So, then you find that the characteristic equation here is dx by dt is equal to b by a, and the compatibility condition is du by dt is c by a. You just have to divide by a to get to this forms. Now, these two conditions written together in a matrix form gives you these two equations. So, gives you this particular matrix. Okay. So, a dou u by dou t plus b dou u by dou x equal to c, which is the partial differential equation itself, and dou u by dou t dt plus dou u by dou x dx equal to du. This is the total definition of the total derivative. From this, if we were to evaluate what is dou u by dou x, or the gradient partial derivative dou u by dou x along the characteristic lines. Okay, along the characteristics lines, we are interested in trying to find this out. So, you can solve this by using Cramer's rule, and we know that we are looking at characteristics lines. So, we get this condition, the bottom is the determinant. So, a dx minus b dt which is 0 along a characteristic line. Similarly, if you take the numerator which is a du minus c dt, that is nothing but the compatibility condition, that is n, numerator is also 0. So, you find that along characteristic lines this gradient is indeterminate. Okay. So, this gives us a method, this trying to find the numerator and the denominator of gradient, and then equating them to be in the 0 by 0 form. This gives us a method to get characteristic lines in general. So, we go ahead and apply this. You can for here example here it is applied for the wave equation itself, dou square u by dou t square minus c square dou square u by dou x square equal to 0. You can follow these steps. It is written as a system of equations, and using the system of equations you find out a set that determinant is equal to 0, or that also is the denominator, and if you set determinant equal to 0, you get two characteristics, which is x minus ct and x plus ct. So, this method, if you follow the method, you also get correct characteristics for the wave equation. Okay. So, in a general wave equation also you will get it. So, we can apply the same principles for the velocity potential equation in supersonic domain. Before we go there, we also have to understand that if you take any particular point in such a general hyperbolic flow or hyperbolic situation, hyperbolic equation, then the particular point, solution at that particular point is influenced by all the regions which are bound by the two characteristics. We saw the wave equation has two characteristics, you can call them C plus and C minus, left running and right running waves. So, there are two characteristics. So, the region that is bounded by the two characteristics is the region which influences a particular point in the domain, in the entire solution domain. So that region is known as the domain of dependence, that is, this particular point is dependent on the initial values or initial values that are within bound by the two characteristics which passes through that particular point. Similarly, if you go ahead and push these characteristics out into the other regions of the flow. So, these characteristics originate from x comma t and then look further in both x and t directions. Then this particular point influences all other points after the particular point or ahead of the particular point only along certain directions which are bound by the again the characteristic curve. So, this is the range of influence for this particular point. If you take any other domain region which is away, which is not bound by the characteristic curves, they are not influenced, or those points are not influencing that particular point. So, they are known as zones of silence. This is true for supersonic cases, where we have seen that a body in supersonic flow, so something of this nature, it affects the flow only along Mach waves. So, if unless this Mach wave passes over a point, for example, a point over here is not influenced at all by a body over here moving at supersonic speeds, m infinity is greater than 1, then this point is not influenced by such a body, while the other point which is lying after the or which has been influenced by the characteristics or Mach waves, there you get the influence of them. Okay. So, this is what is known as domain of dependence and range of influence. So, how to go ahead, now we know that there are these characteristics and we can use to solve them. How do we solve them? Across each along each characteristic there is a compatibility condition. So, you have two things, one is a characteristic equation, the other one is a compatibility condition. You can use two of them together to solve both the flow field as well as what is known as a characteristic net. Okay, so you draw characteristics from one particular point and then you can progress. So, you can progress in forward direction starting from an initial value. So, this kind of an approach is known as forward marching, while you can also have a case where you can take an arbitrary point and try to draw the characteristics back towards the initial position. This kind of solution is inverse marching. It is difficult to do inverse marching if the characteristics keep changing in both x and as both x and t, which is the general case. If it is constant, then yes, it is very easy to do it, but it is not always the case. So, generally forward marching scheme is applied where from the initial values you progress up. So, now let us come for take the specific case of the steady supersonic flow. This is the velocity potential equation written here, right, and you can also take what is du and dv. These are the equations for du and dv. They are functions of only x and y. So, you know that u is dou phi by dou x and v is dou phi by dou y. So, now du is dou u by dou x dx plus dou u by dou y dy. This is dou square phi by dou x square dx plus dou square phi by dou x dou y dy, which is what is written here. So, you have these 3 equations, we can put them into matrix form and find the n by d for say phi x y. Okay. So, for phi x y a gradient we find n by d, and the idea is to put d equal to 0, then you get characteristics equations, and if you put n equal to 0 you get the compatibility condition. Compatibility condition is arrived at. So, that is what is done here. So, you take the denominator, put it equal to 0, you get this particular form, divide the entire equation by dx. So, this becomes a quadratic equation in dy by dx, which is the slope of the characteristic equation or the characteristic lines that can be solved. This is just a solution of a quadratic equation, and you get it in terms of u and v. Okay. So, now this dy by dx is solved in terms of u, v and a square. Is there a way to convert them into more useful form which can yield us something quicker? So, yes, we can do it by converting it into polar coordinates. It is where u is general vector, v is the vector for or v has magnitude of v, vector is v, and u is v cos theta and v is v sin theta. So, we apply this converting it into polar coordinates, then what we get is that we are able to get in terms of cos theta, sin theta and v square by a square. V square by a square is nothing but m square. Okay. And also we know that 1 by m square is nothing but sin square nu. Okay, sin square nu, where nu is the Mach angle. So, we can use those definitions of Mach angle together with these equations, and if you combine all of them together and do some algebraic manipulation, you get that the characteristic equations are defined by tan of theta minus or plus nu. That is the C minus characteristics, one set of characteristics is tan of theta minus nu. The other set, which is known as C plus characteristics, is tan of theta plus nu. So, if you have a general velocity vector v having a certain angle theta, there are two waves, each of them at an angle nu with respect to that point. So, the solution propagates along Mach waves. So, this is something we already know, and therefore, the characteristics are located at theta plus nu and theta minus nu. Okay. Now, what happens to compatibility condition? We can set numerator equal to 0 and along the particular direction dy by dx, where dy by dx is the characteristic curve. We already know what is dy by dx for the characteristic curve. We can solve for this equation, what is dv by du, put u is v cos theta and v is v sin theta. Then what we get is that d theta is equal to plus or minus square root of m square minus 1 dv by v. This particular form should be familiar to all of you by now. Square root of m square minus 1 dv by v is nothing but d nu, where nu is the Prandtl-meyer function. So, you get d theta is equal to plus or minus d nu. So, if you integrate it, you just get the condition. So, if you take the particular slope c minus, that is tan theta minus nu. So, if you look at this, this is a general vector. Okay. So, in the flow field it is at any point x comma y having a Mach number, pressure and temperature. Okay. So, this is the velocity vector, and with respect to this velocity vector there are two characteristics. One goes, both of them go at angles nu. So, let me just revisit the, yeah. So, that nu has to be with respect to the velocity vector. So, it is nu. So, you get theta plus nu here with respect to the horizontal, theta plus nu, and with respect to horizontal this angle is theta minus nu. So, this is C minus characteristics which is colored in green, and the one that is colored in red is C plus characteristic. Along C minus characteristic, the compatibility condition is given by K minus. The K minus is theta plus mu, that nu, that is the Prandtl-meyer function at that Mach number. Similarly, you can take C plus characteristics which is theta plus mu, and along them theta minus nu is constant. So, this is K plus which is theta minus nu, and this is K minus, this is theta plus nu. This is constant along those directions. So, this gives the so for the case of a supersonic 2D flow, we can get the complete integration for, of course, for perfect gases in closed form solutions, and this gives us now simple equations. So, now we have converted a rather daunting looking velocity potential equation to now they have been converted to a set of algebraic equations. Of course, they are in terms of angles and tans and so on. But that can be solved, it is not difficult to solve this. So, so the flow field in the supersonic flow, 2D supersonic flow, can be solved using this set, which we will do in the coming classes for specific cases. There will be follow certain methods known as the unit processes, and we look at supersonic nozzles, how they can be the contour of the wall, how they can be designed based on method of characteristics in the next class. Thank you.